Okay, hi everybody. My name is Thomas, and I'm a PhD with Elisa Chisari. And I would like to show you a work that I've been involved in for quite some time now that has to do with doing fast predictions of model calculations in galaxy clustering. So let's get started. Okay, so yeah, as I said, my talk is about fast methods for correlating galaxies, and this is joint work with Zvonimir Vla and Elisa Chisari. Um, so we are in the large-scale structure era of cosmology, right? So we have DESI, which is a stage 4 survey currently ongoing, and then we also have Euclid and SphereX and other surveys in the pipeline. And basically, these surveys, they collect spectroscopic redshifts of more than 10 million objects. And this allows us to really exploit this powerful statistics from galaxy clustering um, and perform tests of this concordance lambda CDM model in a way that we haven't been able to before. So what we can do with this data set is we can probe, for example, the expansion history of the universe through omega matter or H naught, or the dark energy equation of state, about which there has been a lot of debate lately. And then we also have the growth rate, F sigma 8, which we can probe through redshift space distortions. So one thing that I would like to highlight in this talk is how we can use the information from the scale dependence of the clustering of these galaxies. Okay, so what do we measure in these surveys? Well, we basically measure correlations between galaxy positions, right? So here we have an image from the most recent full shape analysis of the DESI collaboration, where you see measurements of the power spectrum of galaxies, both the monopole and the quadrupole. And basically, so what you do with these galaxy catalogs is you use summary statistics to compress them. And in this case, the summary statistics is the power spectrum, but it could also be the bispectrum, for example, which I've shown here on the right, which would correlate positions of 3 galaxies and then transform it to Fourier space. Okay, um, so how do we then model these galaxies? Well, that's somewhat technical maybe, but let me just give you a brief introduction. So the basic idea is that we know that on large scales, the galaxy overdensity is small because the universe becomes homogeneous on large scales. And if we also think that galaxies formed out of these overdense regions of dark matter through gravitational collapse and so on, then we can assume that the galaxy overdensity is a function of the dark matter overdensity, which is then also small on large scales. And this then basically defines some kind of ordered expansion of the galaxy overdensity, which is called the bias expansion, in terms of the dark matter overdensity. Um, and then these free coefficients, these B's, well, we don't know what they are because we don't know exactly how galaxies form, but we just include them in our model as nuisance parameters, right? So this is then robust on large scales where these densities are small. And for a given set of cosmological parameters, which is the ones that we're interested in, we will compute the dark matter statistics and then plug it into this expansion and compute observables, which are galaxy endpoint functions, basically. Okay, so how do we then model these galaxies? Well, the current state of the art is that we can compute the power spectrum of galaxies, so the 2-point statistics, at next to leading order or one loop level, which means we expand the galaxy density contrast to third order in the dark matter perturbations. Here there's some pictorial representation of what these corrections look like. I will be a bit more detailed in a minute, but yeah, these loop diagrams, if you like, they are just pictorial representations of all of these corrections. So for example, this diagram here on the left, this would be what you get if you correlate the second order correction with the second order correction, and then the other diagram would be the other two. So this power spectrum at next to leading order, this is something that we really know how to do. So there are many publicly available codes like class PT, class 1 loop, Velociraptor, Spybird, and many others that have been cross-checked against one another, and that can compute cosmological parameters from the galaxy power spectrum. So basically what this gives you is some, let's say, percent level constraints on the Hubble parameter, omega matter, sigma 8, but then also some interesting beyond lambda CDM physics like primordial non-Gaussianity or interacting dark energy, for example. But the main thing that I would like to focus on is the fact that beyond the power spectrum at one loop, things get really a lot more complicated. So the next simplest thing that you could consider doing is the galaxy bispectrum at one loop, where you go to fourth order in the galaxy overdensity. And this galaxy bispectrum at one loop has actually been calculated by a number of separate groups. And it turns out to be a potentially interesting probe of primordial non-Gaussianity, and also things like neutrinos and dark energy could be potentially better constrained by the bispectrum. Then another thing that you could consider doing if you're even more ambitious is the fifth order correction, which would give you the power spectrum at two loops. So this would mean that you can model even more scales. So you can add more corrections and therefore get a more accurate model. But doing a full inference in this case, so going from, let's say, the measured power spectrum to these parameters, that has not been done. And the reason why this hasn't been done yet, which is where my approach will come in, is that computing these higher order corrections is extremely challenging from a computational point of view. So in modern cosmology, we do a lot of Bayesian approaches. So we would like to start with some prior on all our parameters, and then we need many, many model evaluations to compute the posterior after including the likelihood, right? And in order to make this practically feasible, we would like to be able to compute model prediction, right? Which would be, given our cosmological parameters, we compute the galaxy power spectrum. We would like to do that in, well, preferably well under a second, and really the faster the better. But for these loop corrections, that's a very difficult thing to do because these theory predictions are very computationally intensive. So the reason why this is because they're integrals over the linear power spectrum. So for every set of cosmological parameters, you have to compute the linear power spectrum and then also do some integral over it, which is an expensive operation. So here's one example where basically, but okay, all these loop corrections look like that, but you have some integral over wave numbers q, and then there is a kernel k, which doesn't depend on the cosmological parameters. That's important. And then there is the linear power spectrum with several linear combinations of these loops, right? So how do you compute this in a quick way? I mean, I can't brute force it. So one idea that people have come up with in the past is, okay, I can decompose this linear power spectrum into some fixed smart basis of functions. And we'll get in a minute to what smart means, but we can choose this basis basically. And if you have some linear decomposition of the power spectrum like this, then actually, because this loop correction is also linear in these power spectra, something nice actually happens, because if I plug this in, then I can write this loop correction as some sum over these cosmology dependence weights, so W of theta, where theta is the cosmology, and then multiplied by some matrix, which I call Sijk in this case. And this matrix is actually independent of cosmology, because my basis doesn't have any cosmology dependence, and neither does this kernel. So that means you can just compute this tensor once and then reuse it at every step of your MCMC. So that's something that people have done in the past in the context of so-called FFTs, where this V of k is a power law, and you can also compute these loops analytically. So these tensors Sijk, at least in some limited cases. So that's the game plan, right? For every cosmology, we would recompute the weights, and then multiply by this pre-computed matrix. So the thing that people have done in the past is they focused on methods for which you can compute analytically this matrix Sijk. However, we argued in this work that this is actually not really necessary. So we came up with a new approach, which we called COBRA. You can read the acronym at the top if you're interested. But basically, we asked ourselves, okay, if we don't care about doing this integration analytically, what's the best possible basis that we could come up with? So we would need the smallest number of basis elements, right? Because that's what will make this matrix multiplication the fastest. So if you ask yourself, what's the lowest number of basis functions into which I could decompose this linear power spectrum? That's actually a mathematically relatively well-defined question. So what you need to do is you need to specify a range of cosmological parameters over which you want to solve this problem. So here's an example. You just choose a range for example, the cold dark matter density and omega b and ns and so forth. And then you choose a grid over which you compute the power spectrum, and then you do a singular value decomposition. As is normal also in machine learning approaches, where you would call this principal component analysis, for example, it's a good idea to normalize your data. So that's this P bar here. But after that, basically doing a singular value decomposition with a predefined rank NB gives you the best possible set of vectors that approximate these power spectrum templates. And then you can also immediately obtain the weights via an orthogonal projection, because this singular value decomposition gives you the basis in an orthogonal form. And this kind of compression, which is very computationally cheap to do, actually turns out to be really efficient as well. So for example, for lambda CDM, we only need about 8 functions to get per mil precision. I've also plotted some of them. And this is really nice, because this allows you to really reduce the size of these matrices compared to other methods like FFT, for example, where you need maybe like 50 or 100. And you can also do this for any kind of loop now, right? We don't rely on doing analytical calculations of these matrices. So what we did concretely in this paper was we took a publicly available code that computes the galaxy power spectrum at one loop, which is this Velociraptors code by Stephen Chen. And we were able to speed it up by roughly a factor of 100 using this COBRA formalism. So it reproduces the original calculation of the galaxy power spectrum at a really negligible error and about 4,000 evaluations per second. And we also constructed an emulator for the linear power spectrum by sort of emulating these weight coefficients W that you saw on the previous slide. So we experimented a little bit with how much this number of basis functions depends, for example, on what parameter ranges you pick, if you think back to this table here. And of course, if you make the ranges wider, then you do need more of these basis functions, but really only a very modest increase in the end. So, I mean, let's say 10 or so is usually really, really good for per mil precision. Okay. So then I'm almost at the end of my talk already, but I do have a bit of a shopping cart, if you like, for the future or the road ahead. So we would like to actually now turn to the cases that were much harder from the outset. So there's the matter power spectrum at 2 loops that we're currently looking into with Enrique Rubira, who's a postdoc at Munich. Yeah, what we've accomplished thus far is we have about a millisecond evaluation of this 2-loop power spectrum for the lambda CDM parameter range that I showed you earlier, where we brute force computed these tensors. And now we would like to actually run an MCMC analysis on some mock data to show that indeed we are now able to do it for the 2-loop power spectrum as well. Then there's also the Galaxy bispectrum at 1 loop, where we're working with Misha Ivanov and Oliver Philcox, and basically redoing their original analysis of validating the Galaxy bispectrum at 1 loop against PT Challenge simulation suite, which is another extremely large n-body simulation that really allows you to sort of pin down any theoretical errors that you might have in these models. And then eventually the plan would be to also update more and more the public code that contains all these endpoint functions at high orders. Okay. So that's it for me already. Thanks for listening to my talk, and I hope to see many of you in the discussion session.